Across modern scientific research, a single mathematical expression has come to function as a professional certificate of discovery, p less than 0.05. The appeal of this threshold is obvious. It takes a chaotic, highly uncertain pile of empirical data and forces it into a simple binary decision. Values below the line point to a genuine effect, and values above it are dismissed as inconclusive noise. But treating evidence as a binary threshold relies on a strict orthogonal error. It demands an answer that the formula itself is incapable of providing. Because this calculation is used as a gatekeeping rule for publishing research, relying on it to separate truth from noise is a primary driver behind the massive replication failures currently plaguing the scientific establishment. To understand the error, we have to separate two different directions of probability. There is the probability of observing specific data, given a model, and there's the probability of a model being true, given the observed data. When researchers run an experiment, they desperately want to know the latter. They want to calculate the probability that their specific hypothesis is true, given the data they just collected. But looking at these flowcharts, what the p-value actually measures goes in the exact opposite direction. It calculates the probability of the data, assuming the hypothesis is already true. Confusing these two distinct directions is a logical flaw known as the transposed conditional fallacy. Concluding that a low p-value proves a hypothesis mathematically guarantees a systematic misinterpretation of scientific evidence. This equation defines the p-value. It represents the probability of obtaining a test statistic at least as extreme as your data. But notice this boundary condition. The calculation is performed entirely assuming the null hypothesis, the model where no effect exists, is true. We can apply this to a real-world scenario. If a study comparing a treatment to a placebo yields a result of p equals 0.03, it absolutely does not mean there is a 3% probability the null hypothesis is true. The correct interpretation is strictly conditional. It means that if the null hypothesis were true, and if you ran this exact experiment over and over, you would see data this incompatible with your model about 3% of the time. The p-value is exclusively a measure of data discrepancy against a specific assumed model. It never provides a direct probability statement about the truth of the hypothesis itself. A p-value never tests a null hypothesis in isolation. It evaluates a fragile compound model, relying on a stack of auxiliary statistical assumptions beneath it. A small p-value might indicate a false null hypothesis, or it might flag that a background assumption failed, tilting the calculation. A common reaction is to assume that increasing a study's sample size will automatically correct for these background errors by drowning out the noise, but the data shows otherwise. When a standard test is applied to data with an unsuitable variance structure, simulations show a massive 26% false positive rate at a sample size of 400 observations. When doubled to 800, the error rate climbs to 37%. Larger samples reduce random sampling error, but they do not eliminate incorrect model structure. As standard errors shrink in a large dataset, a flawed model actually becomes increasingly detectable. A larger sample size can simply produce greater statistical confidence in an entirely incorrect model. This brings us to the most dangerous professional conflation in data analysis, confusing the 5% significance level, known as alpha, with the actual false discovery rate of published findings. To see why these differ, we can track how hypotheses move through testing. This grid represents 1,000 distinct hypotheses being tested by a research field. Assuming standard prior plausibility, only 10% investigate genuine effects.
The remaining 90% are true nulls, where nothing is actually happening. Applying 80% statistical power to the genuine effects, the tests successfully detect 80 of them, 20 are missed. Applying the standard 5% alpha threshold to the 900 true nulls generates false positives. Exactly 5% gives us 45 results that appear significant by pure chance. When an academic journal collects these significant findings, they aggregate the 80 genuine discoveries and 45 false positives into a pool of 125 published results. Look at the mathematical proportion. Out of the 125 significant results, 45 are entirely false. That equates to a 36% false discovery rate. Even in a flawlessly executed testing environment with absolute zero bias or data manipulation, a 5% alpha threshold mathematically yields a literature where over a third of significant discoveries are false. But research is rarely flawlessly executed. Investigators regularly tweak covariates, change exclusion rules, and test different subgroups to find a favorable outcome, a practice known as analytical flexibility. When undisclosed variations occur, multiplicity compounds the baseline error. If a researcher conducts 14 independent tests on true-null hypotheses, the error rate is no longer 5%. The probability that at least one of these 14 parallel tests produces a p-value below 0.05 entirely by chance calculates out to 51.2%. If a researcher runs all 14 analyses but only reports the one result that crossed the threshold, the reader sees a statistically significant finding, but the nominal 5% calibration of that test is completely invalidated. The scientific system generates highly convincing false positives without needing deliberate fraud. It achieves this simply by capitalizing on the hidden mathematics of multiple testing. Recognizing this instability, some institutions have proposed a seemingly obvious reform: demand stronger evidence by lowering the conventional discovery threshold from 0.05 to 0.005. Lowering the threshold reduces false positives under specified assumptions, but fails to solve the root problem. As we see here, drawing a stricter line on the curve cannot fix poor measurement, unrecorded multiplicity, or an implausible underlying model. The data beneath the curve remains just as flawed. A more durable solution requires abandoning binary labels entirely. Instead of declaring a result significant or not significant, researchers must shift to reporting continuous effect estimates alongside their uncertainty intervals. Pairing an estimated effect magnitude with a 95% confidence interval explicitly shows which effect sizes remain compatible with the data. It allows readers to evaluate precision directly, stripping away the false certainty of a solitary p-value. Changing the alpha threshold merely relocates an arbitrary boundary. True statistical remedy requires completely abandoning the illusion that any single metric can safely separate scientific truth from absolute falsehood. This requires structural defenses, like pre-registration. By submitting the analysis plan to peer review before the data is collected, pre-registration explicitly separates exploratory pattern matching from rigorous confirmatory testing. The p-value is not intrinsically meaningless. When models are correctly specified and procedures are strictly followed, it remains a highly specific, mathematically valid measure of data discrepancy. But reliable science requires layering multiple independent checks. It depends on robust experimental design, aggressive model criticism, prior knowledge, and the steady accumulation of direct replication. The p-value has a legitimate role in building a broader evidential argument. But it must never be allowed to substitute for rigorous, holistic scientific judgment.